It's 5:30. Anybody else have any last minute questions before we get cracking? All right, so last time we finished up chapter 10 it was, and now we're going, or excuse me, chapter 9, maybe? Yeah, it was 9. Sorry, I couldn't remember the numbers. I'm working with several different textbooks right now, so the chapters are sort of variable depending on what class I'm in. But anyways, we just finished the chapter on momentum, and we're now in the chapter 10, which is rotational motion. And uh, once we finished momentum, that allowed us to, solve collision problems and stuff like that. But we were still short on some of the stuff we were doing in Newtonian physics. Like we could predict, a point particle being launched as a projectile. We could predict where it would land and, what the actual trajectory of it was. We could give x of t, we could give y of t for any points in time. But if the object had a physical size to it as opposed to it being a point particle, we weren't really prepared to do anything about that. So, what we need to address that is one, we take everything that we've learned about Newtonian physics for point particles, and those still apply, but they apply specifically to the center of mass of an object. So, if you're actually throwing, for instance, this pin as opposed to a point particle, which could be treated like a BB or something like that, then what we're going to see is when I throw this, it'll spin like that. And in fact, you'll see that there'll be one point in this pin that will sort of everything will rotate around it like that, even though its trajectory is going like this. Everything else will rotate around that. Well, once we figure out how the center of mass moves, which we have, now we can go about saying, okay, well, if I assume that, horizontal is theta equals 0, then I could measure this angle right here, and that angle would give me theta as a function of time. And if I knew when I threw the pin exactly what theta position it was in and exactly what speed, angular speed it had, which we call omega, then I could also figure out exactly what its orientation would be at any point in time later. So not only would I more accurately know exactly where it's going to land, I could actually predict what its orientation will be when it does land, because of course it could land where it just flies like this and then it'll hit when this part hits. But that's not what the center of mass calculation gives us. The center of mass calculation gives us when the center of mass hits there. So if it's in this orientation, then it's going to spin like that really quickly, and we'd have to address that and so on and so forth. So, in order for us to make sense of how this rotation goes, we need to understand rotational motion, and that's what chapter 10 is about. Chapter 10 all starts with a very fundamental equation that hopefully you know from trig, and that is I call it the definition of radian measure. So let me go ahead and share my screen with you guys so we can all see the same thing here. Hopefully this will pop up in a second. Okay, so now you're looking at my screen like I am. I'm going to draw. Whoa, Nelly, I don't know what happened there. I mean, I know what happened, but I don't know why it happened. Uh, this is weird. All of a sudden, my tools are not being shown on my iPad, and no, that's not right either. Maybe I'd push this. There you go. Okay. There's a little button I hadn't seen. So what I'm going to do is draw a circle. And what we can do is we can imagine that this is the radius r, and that's another radius r. And if we imagine a angle being swept out by this radial line, that angle could be theta, then the actual measured arc length, the distance along this bent curve all the way down to here, not the S that I actually drew, but actually on the circumference of the circle. If this was the radius r and that angle subtended by that S would be given by S is equal to r times theta, and we think of that as the definition of radians. So for instance, we might think that 360 degrees would correspond to an arc length equal to the circumference. So 360 degrees implies S is equal to C, which is 2 pi times R, but that's also equal to R times theta, which implies theta is equal to 2 pi radians is also equal to 360 degrees. So what that gives us is a conversion factor. Remember, anytime you can write a fraction where the numerator is equal to the denominator, then that's a conversion factor, if you will, and we can write that as 2 pi radians divided by 360 degrees. Of course, we could also write it the other way around, and we could even get rid of the common factor of 2 and say it's 180 degrees divided by pi radians. And you'd also see that 1 radian is approximately equal to 57.3 degrees. Again, in that case, you could just take 180 and divide it by 3.14159, and you get that 57.3 roughly. It's actually a non-terminating decimal, of course. But that little relationship between the arc length and the angle subtended and the radius is the beginnings of rotational motion. Once you have that, for instance, you can take d by dt of S is equal to R times theta, and that's going to become ds over dt. If we assume R is a constant, that'll just stay there, and we'll get d omega, or excuse me, d theta over dt. Now, we define this ds over dt. You can see that's a measured distance along the arc of a circle. So that's literally just your distance traveled, and therefore you could easily relate it to speed, but it's also related to velocity. So we could say this is equivalent to V equals R omega, where omega is defined to be d theta over dt. Now, we could also take the derivative of this function, and we would get dv over dt is equal to r d omega over dt. And that's the equivalent of saying A, and this specifically is the tangent acceleration, just like this is the tangent velocity, is equal to R times alpha. So what we have now is some very important equations. We've got S is equal to R times theta. We've got V tangent is equal to R times omega. And we've got A tangent is equal to R times alpha. From that, it turns out we can go ahead and take all of our definitions that we had in chapter 2 when we were studying kinematics, and we can sort of map out exactly what that is. So, for instance, one of the first things, I'm skipping speed here, I'm just going straight to velocity, but one of the first things we did was velocity is equal to delta x over delta t. And of course, this also gave you, and this was the average velocity, I should say, and this also gave you x is equal to x0 plus v bar times t. Notice the only change I did from the left side of this little blue arrow to the right side is I changed delta t to just be called t. Similarly, we could say the average acceleration was delta v over delta t, and that would give us the equation v is equal to v0 plus alpha bar t, again changing the t into t from delta t. Of course, we also have the equivalent, which was the instantaneous velocity, is dx or dr over dt. And we also had a is equal to dv dt, which is d2x over dt squared. In addition to that, we were able to come up with, for instance, a velocity average, if the acceleration was a constant, is just v1 plus v2 divided by 2. Additionally, if the acceleration was a constant, we found that x could be given by 1 half at squared plus v0t plus x0. And finally, we found that v squared is equal to v0 squared plus 2a x minus x0. Now, if we notice something that is very helpful here, for instance, one thing we can say x is going to become either s or x is going to go to theta. In other words, theta is going to play the exact same role as x in rotational motion. There is a time where x will play the role of the arc length too, but we'll leave that be for right now. We also know that v is going to become omega, and we know that a is going to become alpha. From that, we can get these equations, which are omega prime is equal to delta theta over delta t, and that gives us theta is equal to theta 0 plus omega prime t. Similarly, we get alpha bar is equal to delta omega over delta t, and that gives us, of course, omega is equal to omega 0 plus alpha prime t. Notice again, I'm changing the delta t to just t in those two expressions. We also have alpha is going to be d theta over dt, or excuse me, omega is going to be d theta over dt. So that's the instantaneous one. But then the acceleration could be d omega over dt, which is also d2 theta over dt squared. We also end up getting something along the lines of omega bar would equal omega 1 plus omega 2 over 2. And again, these require a equals a constant. And on this side, these are going to require alpha equals a constant. And notice I mixed the colors on there for some reason, but I wanted to make sure it was consistent. So I drew the little arrows so y'all know what I was talking about here. Now, the equivalent of theta, or excuse me, of x is going to become theta is equal to 1 half alpha t squared plus omega 0 t plus theta 0, and omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. The whole point of me showing you all this stuff is that you understand that we're not learning any new material here other than learning new names for the rotational analogs of the linear things. So, for instance, we already took the time to learn what X was, what V was, what A was, what time is, what dVdt is, and all that sort of stuff. Now we've got a set of new variables that in place of X, we're going to use theta, which in principle could be measured in radians and will always work in radians, but sometimes it'll work in other things. We're going to have, instead of V, we're going to have omega. Instead of A, we're going to have alpha. And then there's relationships between them that obviously we didn't have in linear motion because we only had one equation. So the S equals R times theta, and the V equals R omega, and the A tan equals R alpha. Those are equations that obviously you wouldn't have in linear motion. But it goes further than that. In fact, in addition to these variables, we're going to have mass is going to become something like the moment of inertia. And it's somewhat like it, but it literally doesn't even have the same units. It has units of kilogram meter squared is the moment of inertia. Instead of force, we're going to have something again with not even the same units. We're going to have torque, and that's a Greek letter tau, by the way. And instead of momentum, which was P equals mv, we're going to have angular momentum, which is L equals I omega. So all of that stuff is going to continue, but now we know, hey, I've already learned how to apply these equations that look just like the rotational ones. So you just have to apply them the same way you did it when you were doing linear motion. Now that I've given you all that, we're going to start off by doing some very specific examples, the examples in the textbook. And I'm just going through them one by one. I'll skip a few because I want to make sure I get through some of the more difficult quantities and examples as opposed to the easy ones. But does anybody have any questions on this so far?
Uh, could you move the bottom up a little? I can't tell if that's an R or a D that equals M times V.
Oh, that's a P is in, yeah.
Oh, okay. I couldn't see there was a thing
It
in there.
prob
Okay.
Yeah, I blew the screen up and it pushed it down. This one's going to be L is equal to I times omega, and we'll talk a little bit about this, but there is a rotational analog to the directions for these vectors. For instance, we can treat the angular velocity, which is what I call omega. It's also called angular frequency. We can treat it as a vector quantity, but it turns out it's going to be a pseudo vector, and your book explains that, but I just want to point it out to you now. So let's look at, for instance, example 10.1. And I'm using the textbook here, so this is a good time for you to actually have the textbook out if you do, so you can read it, but I'll read the example to you as well. Specifically, it says, example 10.1, bike wheel. A bike wheel rotates 4.50 revolutions. How many radians has it rotated? So what we're given is, and I'm jumping to a conclusion here, but a bike wheel rotates 4.50 rotations. That's sort of the total distance that it traveled, but it's distance in like degrees or revolutions or something like that. So that tells me it's somewhat like my x variable. And what we discovered was the x variable will be replaced by theta. So I'm going to say theta is equal to 4.50 revolutions. Now, what I want you to think about is when things rotate, a rotation, for instance, I don't know why I have a light bulb here, but I do. So, uh, this light bulb has a 40 on it. And when I rotate from here to here, that's roughly a 360-degree rotation. That's also called one cycle. That's also called one revolution. Okay. So that tells me that a revolution is equal to 360 degrees and it's also equal to 2 pi radians. And what we're asked to find is theta in radians. So theta equals 4.50 revolutions. This can be thought of as a unit conversion. So I'm going to go ahead and write that as if it's a fraction because that's what we learned in chapter one is we're going to have to multiply by fractions. So you might as well put it over one so you don't get confused what's the numerator, what's the denominator. And in this case, I've just explained to you that one revolution is the equivalent of 360 degrees, which is also the equivalent of 2 pi radians. So I'm going to go ahead and write 2 pi radians right here. And you see that the revolution cancels out, excuse me. And we end up getting 4.5 times 2 pi, which is 9.0 pi radians. Now that's actually perfectly fine. And in fact, it's quite nice to express radians in terms of pi uh, or 2 pi or something like that. But it's also helpful to know the decimal value. So I'm going to do 9 times 3.14159. And that gives me about 28 point, and we only had two sig figs, or actually we had three sig figs, so it's 28.2, and I'll give one extra sig fig, which is a 7, and that's radians. So this is the answer. It's either 9.0 pi radians or it's 28.27 radians. Anybody have any questions on that? So now we're going to do the next example, which is example, oops, I had it on the automatic draw thing, and it did not like that. So example 10-2. Example 10-2 says birds of prey in radians. So this is something that's a problem that is something we're teaching you something that you're going to be able to use repeatedly, and you'll see it in a second. But basically, what it says: birds of prey in radians. A particular bird's eye can just distinguish objects that subtend an angle no smaller than about 3 times 10 to the negative fourth radians. A, how many degrees is this? And B, how small an object can the bird distinguish when flying at a height of 100 meters? So that part B is where I'm going to show you something that you can use from here on out. For starters, what I'm going to do is write that delta theta. I'm putting a delta on it because I'm thinking of the theta is from here to here. So I'm really looking at a difference in degrees. So what we're thinking is there's some angle between let's say the line connecting the eyeball of a bird to the tail end of a bunny rabbit, and then there's another ray that comes from the eyeball of the bird to the head of the bunny rabbit. And if the angle between those two lines is 3 times 10 to the negative fourth radians are bigger, then the bird should be able to see that, oh, this ends the tail, this ends the head, and they're distinctly different. If it's smaller than that, then they aren't going to be able to resolve it. That's called resolution. Okay. So it turns out like the human eye, I think we see on the order of half an arc second or half an arc. Half a degree, something like that. Whereas obviously the eagles is much better. But delta theta is 3.0 times 10 to the negative fourth radians. And part A, they want to know what that is in degrees. So delta theta equals 3.0 times 10 to the negative fourth. And actually, the point zero, they only gave us one sig fig, so I'm not technically being correct by calling it 3.0. That's why I went ahead and underlined the zero. It is a unit conversion, so I put it over 1. And now I'm going to use the fact that pi radians is equal to 180 degrees. Now we further divide degrees into a 60th of a degree is a arc minute, and a 60th of an arc minute is an arc second. So we could go further in that, and I will just to show you what I mean. But let's start off with this: 3 times 10 to the negative fourth times 180. And now I'm going to divide that by 3.14159, and that gives me 0.0172 degrees. But if I multiplied that by 60, then I could get it in arc minutes. So times 60 gives me 1.031, and the symbol for arc minutes is a single dash or a single apostrophe like that. Just like that's also the mark for a foot, and an inch is two of them. Now, if I multiplied the decimal part of this by 60 again, then I could convert that 0.031 to arc seconds. And that would be 1 arc minute, and then 0.031 times 60, and I carried an extra digit there. That is 1.878 arc minute or arc seconds. So basically what we have is the angular measure is 0.0172 degrees, which also is about 1.031 arc minutes, but that's also 1 arc minute plus 1.8 arc seconds. So again, just to show you where that came from, I just wanted to show you in case you have to do any calculations with degrees that are smaller or angles that are smaller than degrees. So this is times 60, and that's times 60, and that's 60 arc minutes per degree. And then this part gives this one, and this is times 60, and that was supposed to be a single mark up there, times, why do I keep writing 16? Am I just hearing myself and thinking it says 16? I don't know. All right, so let me do this, fix this a little bit. Got that. So that's an arc minute per degree, and this is times 60 arc seconds per minute. So that's how I got that. Just wanted to make sure everybody knew how I did it. So here's
Why
part.
did you
Go ahead.
put the one and the arc second before the minutes, or
But
the minute before the second?
sort of the same way you do when you'd say a movie is 2 hours and 20 minutes long. You could say the movie is 2.33333333 hours, but if you didn't want to do that, you'd say it's 2 hours and then you take the 0.3333 and multiply that by or divide that by 60. And when you did that, that would actually give you the fractional part of a minute. So the that would give you the 20 minutes. So you call it 2 hours and 20 minutes. The same thing I did here. So I multiplied the degrees by 60, and that gave me the arc minutes. And then I
Yeah.
took the fractional part, which was what's in excess of one arc minute, and multiplied that by 60 to get the arc seconds.
I see. Okay, I thought you were multiplying the whole thing, not just the zero, three,
Yeah,
one.
just
Okay,
yeah,
that's right. Okay.
that's why I drew
All
those
right.
little green arrows just in case there was some confusion about that. But yeah, I get you.
Okay. Thank
When I make up stuff in my head, you're supposed to completely understand it, even though I made it up in my own head. I didn't tell you about it, right? All right, so let's look at part B, and this is the part that I was telling you about. So I'm going to start off by drawing a decent sized circle so we can make some sense of what I'm talking about here. I'm going to let the program make the circle a little better than I can, a whole lot better. Okay, so what we're picturing here is the eagle's eye or the bird's eye is right here, say, and in principle, the eyeball will look down and see the tail, say, of a rabbit or a deer or something like that, and then it'll look down and see the head of it. And this angle right here will be theta, or it could be delta theta, but I'm just calling it theta right now. And the big thing is, this is the radius of the circle, which is on the order of 100 meters. Okay, so this is the eagle looking down on it, on something, or the bird of prey looking down on it. Now, what I see subtending that angle is the little red arc that would be like S. Well, there's also a chord length that is the straight line that connects the two dots, and the chord length is approximately equal to the arc length when the angle is small. So chord length, and I want to say that CHORD. Let me double check. I hate to say that. It's been so long since I typed that out. Yep, it is chord CHORD. I don't know why I wrote CORD. Chord length is approximately equal to arc length when theta is small. So just to give you an idea of what we're talking about, if this was an arc, so this could be the angle phi, say, this would be the chord length or the chord, and this would be the arc length. So that's what I mean there. Now, with that in mind, we can just say, well, the arc length is approximately equal to the chord length, so the actual measurement of the creature, which I'll call L, is approximately equal to S. So we'll say L is approximately equal to S, which equals R times delta theta, or since I wrote it in there, I could have just called it theta. But let me go ahead and change it to delta theta since I had called it delta theta up top anyways. So I'm going to say this is the angle delta theta. Okay. So with that in mind, I can see that the result would be 100 meters times. Now remember, in order for S equals R times theta to work, you actually have to have this in radians. You can't put it in degrees. So this is going to be 3.0 times 10 to the negative fourth radians. And 100 times that is going to give us 3.0 times 10 to the negative 2 meters, which is 0.030 meters. R L is equal to 3 centimeters. So that means at 100 meters away, a bird of prey with this type of eyesight can actually tell the difference between two objects that are 3 centimeters apart. That's a pretty big deal. Like if you had two rocks, well, if you had a rock and then you had 3 centimeters away, you had a piece of food. The bird could discern the difference between the rock and the piece of food. He wouldn't see them as one big object. This is not unlike when you're driving at night on a really long straight road when a car in the distance is first seen, you don't really know if it's a car or a motorcycle because you can't see the difference. You can't see the two headlights. You just see a single light. Once they get close enough, if it is a car with two working headlights, then all of a sudden the two headlights will pop apart. That's because it's gotten within your angular resolution of your particular eyes. Now, again, human eyes have a very particular resolution, but then that varies greatly from one human to the other because of various, maladies with our eyes or whatever. But this trick of using the arc length as approximately equal to the chord length is something we use repeatedly. So, anybody have any questions on that? All right. So, yes, at 100 meters away, in principle, this particular bird of prey, which might be a hawk or a falcon or an eagle or whatever, this one could see something that's 3 centimeters across. That's pretty impressive. Now, let's look at another example. This one is example 10.3. I don't know why it did that, but now I'm fixing it. Okay. So, example 10.3. Now, this one says on a rotating carousel or merry-go-round, one child sits on a horse near the outer edge, another child sits on a lion halfway out from the center. Which child has the greater linear velocity? Which child has the greater angular velocity? So I'm going to again start off with drawing a circle, and I'm going to let this program draw it better for me. Whoa, that was so bad it decided to draw an oval. That's pretty good. Okay, so what we're looking at here is a radius r, and then what we're going to imagine is right here at a distance of r over 2, that is going to be our lion. But also out here at a distance of r, that's going to be our horse. Now, the big thing you got to understand is when you rotate something rigid like this merry-go-round, then it's going to rotate in such a way that two things that are side by side are going to stay side by side. So, for instance, if you look at this light bulb, which says 40 on it, uh, when we actually go to rotate it, the zero's always going to be behind the four. So if I turn it this way, you're still going to see the zero and the four make a line, or the zero and the four make another line, or the zero and the four make another line, so on and so forth. The main thing that I'm pointing out here is this merry-go-round is a rigid body. So the lion is always going to be dead center between the horse and the center of the merry-go-round. Because of that, when the horse makes a full revolution, the lion's going to make a full revolution as well. So that tells you theta 1, theta for the lion, is equal to theta 2, theta for the horse. But not only that, if the lion makes a rotation of theta 1 in a time t1, then the horse is going to make that same rotation theta 1 over the same amount of time t1. That's just the nature of it being rigid. So from that we can reach the conclusion that omega for the horse is equal to omega for the lion. Now we use the equations that I told you that came from S is equal to R times theta. That gave us V tangent is equal to R times omega. And that's one we're actually going to use. There's another one that we're not going to use right now, and that's A tangent is equal to R times alpha. But the V tangent we are going to use. So we'll say V horse is equal to R times omega, where omega is the angular velocity at which this thing rotates. It would be measured like in radians per second or revolutions per minute. And similarly, the velocity of the lion would be R over 2 times omega. So you can see that the velocity of the horse is going to be twice the velocity of the lion. That's how they're related. Anybody have any questions with that? Now, if you've ever done any water skiing or seen water skiing on TV, I used to do that quite a bit myself. One of the things that you learn quickly is when a boat is taking a turn, the boat might take a turn that's 100 foot in radius, and the boat speedometer might be reading 30 miles per hour because the boat is going 30 miles per hour. But if you take and swing out to the outside on the end of a ski rope that's maybe 30 feet long or 33 feet long, then what you'd see is you're actually making a circle too, only your circle is 100 feet plus 33 feet. So that's 133 feet. And therefore, your speed is a third faster than the boat speed. So even though the boat's going 30 miles per hour, you can actually go 40 miles per hour because you're getting uh, an extra 33 feet of radius out of it, and you both, if you're literally staying beside the boat, then you're acting like a rigid body. So the boat is making a particular rotation, let's say from going due north to going due west. The same time the skier is going due north to due west. And in that sense, they're acting like a rigid body. So that means the omegas for the boat and for the water skier are the same. So just like the horse and the lion, their omegas are going to be the same, but their velocity is going to be markedly higher. That is exactly why, for instance, if you're doing the water skiing championship where you actually are jumping and trying to get the farthest jump you can, you generally try to swing out really far from the boat if the boat were taking a turn, for instance. But either way, you could still use it to gain more speed because you can push on your skis just enough where you can force yourself to move out from behind the boat, and by leaning and basically applying force to the water, you can force yourself to come up and get going even a little bit faster than the boat. And therefore, when you hit the ramp, you'll actually go further than something that was just as going as fast as the boat was. So hopefully between all that, you have some familiarity with something about this. Okay. It is potentially extremely dangerous, uh, swinging out like that. So just be careful. Like if you're ever letting, I've seen people that'll pull snow skiers back behind trucks on ropes. The same thing applies there, only the damage that happens when you hit a piece of pavement or a car or a tree is much worse than when you hit water, usually. When I was teaching myself to barefoot, I did discover that, 85 miles per hour, you might as well hit the concrete because it hurts really bad when the water hits you at that speed. All right. Uh, that was part A. So the tangential velocity are definitely different. But for part B, they wanted to know what child will have the greater angular velocity. And in this case, the omega for the horse is equal to the omega for the lion. And that's the right answer for part B. Any questions on that? All right. Let's go to another example. This is example 10.4. Now, this example says a carousel is initially at rest at t equals 0. It is given a constant angular acceleration, alpha equals 0.060 radians per second, which increases its angular velocity for 8.0 seconds. At t equals 8.0 seconds, determine the magnitude of the following quantities. A, the angular velocity of the carousel. B, the linear velocity of a child located 5.5 meters from the center. C, the tangential linear acceleration of that child. D, the centripetal acceleration of the child. And and E, the total linear acceleration. Okay. So what I'm going to make a point of noting here is V tangent is equal to R times omega, and A tangent is equal to R times alpha. And then A centripetal is equal to V squared over R, but also A, the total acceleration, is A tangential plus A radial. Okay. Centripetal means radially inward, and radial just means radially outward. Okay. So you might want to assign a negative if it's centripetal as opposed to radial, but it doesn't matter. The main thing is we're going to treat the two as vectors, and then we're going to work out a vector quantity for the acceleration. What they did give us, of course, was that a carousel was initially at rest. Again, they didn't explicitly tell us a number, but what they did was allow us to reach the conclusion that V0 is also equal to omega 0, and that's 0. Notice I didn't put units on it because I tried to be quick and write V equals omega equals 0. If I put the units on it, it'd be wrong because the units of V are different from the units of omega. Omega, like I said, should have degrees per second, radians per second, revolutions per minute, revolutions per second. V would have meters per second or something like that. Uh, and this is at t equals 0. But also, what we know is the acceleration alpha is equal to 0.060, and that's radians per second every second. And that's going to increase its angular velocity. So for part A, we want to know the angular velocity of the carousel. So A, we want omega equals question mark. B, they're saying the linear velocity of the child. So R was equal to 5.5 meters. So we want V tangent of the child is T. This is at T equals 8.0 seconds. And that includes this one and this one. They're all supposed to be considered at 8.0 seconds. So hopefully we can you can read that. C, the tangential linear acceleration of the child. So we want A tan, which I'm just going to call AT, equals question mark again at 8.0 seconds. D, we want the centripetal acceleration, that's AC, equals question mark at 8.0 seconds. And then E, we want A total, which is a vector quantity. Okay. And again, that's at 8.0 seconds. So starting with A, what we want to know is the angular velocity. What we do know is we know the acceleration is alpha equals 0.060. And if we were told something started from rest and had an acceleration of 0.060 meters per second every second and did that for 8 seconds, then we would look for a very specific equation to use. And I think if we were doing linear motion, you would probably suggest that we'd use this one. The v is equal to the initial velocity plus the average velocity times time. But if the acceleration, or excuse me, the average acceleration times time, but if the average acceleration is the constant acceleration, then you don't even have to have the average. You're just going to use that. So the idea that this is what we'd use, if excuse me, if this was a whoa, that's supposed to be an A anyways. What a crackhead. Uh, the idea that this is what we're supposed to use in linear motion should let you know that we're going to use the equivalent equation in circular motion. So it's that. And you can literally do all of your physics problems in this chapter that way. You just figure out what kinematic equation I'd use from chapter two, and then use the exact analogous one in this problem. So that's what I'm going to do here. I'm going to say omega is equal to omega 0 plus alpha t. In this case, the alpha is a constant, so we don't even have to write the average there. So this is going to be 0 plus 0.060 radians per second every second times 8.0 seconds. And 8 times zero point zero 0.06 is 0.480, and that's radians per second equals omega at 8.0 seconds. So I'm going to go ahead and box that off because that's one of our answers we were asked for, and that's part A. Any question on that part? Okay, for part B, they want to know the tangential velocity, and what we know is V tangential is equal to R times omega. So we just put in the 5.5 meters, and we're going to multiply that by the angular velocity, which is 0.480 radians per second. So when I do that math, I get 5.5 times 0.48. That gives me 2.64. Notice I'm carrying one extra digit that's not significant. And that's meters per second equals V tangent at 8.0 seconds. So there's part B. Now we go to part C. In part C, they want to know the tangential acceleration. So that's actually a lot easier than you might think. Tangential acceleration, A sub t, is just equal to R times alpha. So all we have to do is put in the 5.5 meters and the 0.060 radians per second every second. And that is 5.5 times zero point zero 0.06 is 0.330, and that is meters per second every second. Notice how I just threw away the radian. If you look at S equals R times theta and you solve for theta, you'd see theta is S over R. You know S and R have to have the same unit, so you're literally looking at theta as a dimensionless quantity. And that's truly what radians are. They are not angular measure that has a unit. They're actually just a pure number. So you can bring in the word radian anytime you want and put out the word radian anytime you want, just about. And this again is at 8.0 seconds. So I'll box this off. That's our AT, our tangential acceleration, at 8.0 seconds. Now we're looking for part D, which is centripetal acceleration. So part D, A centripetal is equal to V squared over R, and our V we already worked out was 2.64 meters per second. That quantity is going to be squared, and we're going to divide it by 5.5 meters divided by 5.5, and that gives me 1.27 That's one extra digit, by the way. So that's 1.27 meters per second every second is equal to a centripetal at 8.0 seconds. I'm going to box that off, and that's part D, and this one was part C. Now, finally, we want a total, and as I told you, you you can always break up any vector into perpendicular components, and what we're doing here is we're saying all accelerations can be broken down into tangential acceleration, which is sort of what your speedometer reads if you've got your steering wheel of your car tied up so that it stays in one particular angle so that the car is just going in a single circle. Ideally, if you did it right, it would actually trace out the same path over and over again. If that was the case, if you had your steering wheel turned that way, every time you hit the accelerator, you would speed up or slow down. If you took the amount that you sped up or the amount that you slowed down, in other words, V final minus V initial, and divided by the time taken, that would be your tangential acceleration. The centripetal acceleration is the acceleration that's required to maintain that circle. So that's the v squared over r we're talking about. But just so you'll know, that's what those are. So now I'm going to try to render this in a vector situation. So I'll put E here, and I'm going to draw a circle for starters, just to give us an idea of what we're looking at. So there's our circle. And what we're imagining here is there could be, for instance, an object right here, and this is going to be a radial line. And what we have is a tangential acceleration. Oops. Tangential acceleration, a tangent. But we also have a radial, i.e., centripetal acceleration, that's about 4 times as big. So I actually drew that AT a little bigger than it should have been. I'm going to draw this like that and say that's close enough to about 4 times as big. And this is AC. So we know that when two vectors are tail to tail, the sum of those vectors is found by completing the parallelogram. And what we're going to get is this vector right here. So this is A total, that vector right there, which actually went really bad when I tried to fill in that circle or fill in that arrowhead. So now I'm going to make it much worse. That's probably what's going to happen. All right, so I got this. Oop, that's the wrong color. I got this, and I got this like that. Okay, so now you can see what that vector is. And in fact, we might want to know specifically, let's say this angle right here is the theta. So now we can see that A total, once we realize that A tangential and A centripetal are both perpendicular to each other, then we can see that A total, according to the Pythagorean theorem, is A tangential squared plus A, in this case, centripetal squared. We would have normally called it AR, but that's acceptable as well. So it's going to be the square root, and of course, lengths of vectors are always positive, so we're not considering the negative square root. But in this case, we're going to say the tangential part, which is 0.330 meters per second every second. That quantity is going to be squared plus 1.27 meters per second, and that quantity is going to be squared as well. And that's going to give us 0.33 squared plus 1.27 squared. That gives me the square root of 1.722 meters squared seconds to the fourth power. And when I take the square root of that, I get 1.31 meters per second every second is equal to a total. I'm actually not going to put that because I can't fit the word total in there. So that's our acceleration's magnitude. And the angle theta can be given by our tangent function. So theta is equal to the tangent inverse of opposite, which is a tangent, that's 0.330, over adjacent, which is AC, that's 1.27, leaving the units off because they're going to cancel out anyways. Now I take the inverse tangent, shift tangent, 0.33 divided by 1.27, close parentheses. This gives me 14.56 degrees. And obviously, that's quite a bit more than what we're supposed to have in terms of sig figs. But the main thing is now we know what our total acceleration is. Anybody have any questions on that?
Just one. We kept specifying everything was at 8 seconds, but it
Mhm.
never actually came into play in any of that. Was that just an example of what we could see, or was there a
Yeah,
point to the eight
when you look at
seconds?
the next one, you'll see a little bit more of a tie-in. I just wanted to make sure you knew that we the main thing we did do was calculate what the angular velocity would be after 8 seconds. So anything that used the angular velocity, which is the v tangential, had to use it, and then the AC, which used the v tangential, had to use it. So specifically, you couldn't have got part D as in dog nor part B as in boy without the 8 second part of the calculation. That being said, the AT was completely irrelevant. Didn't matter that it was 8 seconds or not. It would have been the same way either way. Does
Okay.
that help?
Yes.
Yeah, sometimes the 8 seconds is real. I mean, how much time has passed is really relevant. Sometimes it's not. And you'll see that. And I think it's the very next example. Let's see. Yeah, here it is. Example 10.5. So let's move on. I'm going to do example 10.5. And it says a disk of radius r equals 3.0 meters rotates at an angular velocity omega equals 1.6 plus 1.2 t, all that measured in radians per second, where t is in seconds. At the instant t equals 2.0 seconds, determine A, the angular acceleration, B, the speed v, and components of the acceleration A of a point on the edge of the disk. So what we want to know is at t equals 2.0 seconds, we want to know A, what is the angular acceleration? So we want to know alpha equals question mark. And B, at that time, we would like to know the speed V, and that's specifically the tangential speed. We also want to know the components of the acceleration. So we want to know A tangent and we want to know A radial. So that's what we're trying to figure out here. So let's go ahead and use what we're doing here. The first thing we want to do is figure out what alpha is, and alpha is equal to d omega over dt. So that's going to be d by dt of 1.6 plus 1.2 t. Noticing the units come out in radians per second, but when I take the derivative of all this, I'm just going to get 1.2 radians per. Now, in this case, it's going to be, you have to figure out what the units of the 1.2 and the 1.6 is. You know that after you multiply 1.2 times t, you should have units of radians per second, and you know that t is in units of seconds. So can you guess what the units of 1.2 are? Do you see that it has to be seconds squared? You can look at that two ways. One, the d by dt suggests you're dividing it by seconds, so that's going to bring that in. The other thing is that the 1.2 has to be multiplied by seconds and spit out radians per second. So the only way that could happen is if there was already a second squared in the bottom. So notice that this is true at all times, not
Wait, why is it just 1.2? Is it just
the
because
derivative of
there's no
1.6 plus 1.2t.
oh yeah, oh, because there's nothing after the 1.6, so getting the derivative.
Exactly.
Okay.
So this is one of those cases where they told us specifically at 2 seconds, but we calculated the acceleration and it turns out to be a constant. So it's going to be that acceleration at all time, not just the 2.0 seconds. So in this case, this is going to be another one that's kind of weird. But now we can go ahead and write down that alpha is equal to 1.2 radians per second every second, and I'll box that off. Now for part B, we want to know V. So V tangential is equal to R times omega, but we want it at 2.0 seconds. So we've got to evaluate omega at 2.0 seconds, which is going to be 1.6 plus 1.2 times 2.0. And you can see 2 times 2 times 1.2 gives me 2.4. 2.4 plus 1.6 gives me 4.0. So that's going to be 4.00. And that comes out in radians per second because that's the way the definition of the formula omega was defined. So now I have the omega. Now I can calculate the VT is equal to 3.0. Notice I added an extra digit that's not a sig fig, times the omega, or excuse me, times the omega, which is 4.00 radians per second. So now you can see that I get 12.0 meters per second is the angular or is the tangential velocity at t equals 2.0 seconds. That makes sense to everyone? A tangent, on the other hand, is going to be equal to r times alpha, like that, but that doesn't necessarily help us that much. Uh, Actually, yeah, it does, because we know the r and we know that. So in this case, it's going to be 3.0. Again, I'm adding an extra digit that's not a sig fig, but I knew it was zero. So that's the zero, and then times the alpha, which we found out was a constant. So that's 1.2 radians per second per second. So in this case, we get 3 times 1.2, which is 3.60 extra digit there. In this case, again, we're just going to throw the radians away because we're allowed to do that, and we're just going to get meters per second every second is equal to a tangential at 2.0 seconds. In this case, again, it's technically the answer at 2.0 seconds, but we would have got the same answer at any other time too because the acceleration is a constant. Now we're going to do a radial, and that's equal to v squared over r. We've already figured out that the velocity is 12.0 meters per second at 2 seconds. So I'm going to square that, and then I'm going to divide it by 3.0 meters. 12 squared is 144. 3 goes into 120 40 times. Then it goes another 8 into 24, so that's 48. So the centripetal acceleration is radially inward, and it's going to be 48.0 meters per second every second is equal to A radial. Now, in this case, you can see that the angle would be quite a bit different because you got one component's 48 and the other one's only 3.6. So that's quite a bit bigger difference. So the angle would be even smaller than the 15 degrees we got last time. Anybody have any questions on that? All right, so that's just some rather quick calculations of various quantities and kinematics, and it's very straightforward. I want to get on to the other stuff. Your book does talk about pseudo vectors and axial vectors. You want to learn that. The main thing is when a disk is rotating this way, you imagine your right hand here. And you imagine your fingers curling around in the same direction that the disk is rotating. So if the disk is rotating this way, which from above looks like counterclockwise, then I want my fingers to curl around counterclockwise, and I'm using my right hand, and that forces my thumb to point up. So what that means is if I'm looking at something that's rotating counterclockwise, then by looking at it counterclockwise, the vector that represents the angular velocity is pointing right at me. Whereas if it's rotating clockwise, the vectors pointing away from me. That's the way we define the angular velocity vectors, and they're called axial vectors. But the big thing is they'll show you in Figure 1010 if you look at a particle with its velocity, and then you look at a particle's image with its velocity's image in a mirror, you see they're both the same. But when you look at a disk in reality rotating, say, counterclockwise, and then you look at the mirror image of that disk rotating, you'll see in the image it's actually rotating counterclockwise when in the real object it's rotating clockwise. So they actually reversed, and because of that, the image actually has the omega pointing to the left, whereas the actual disk has the omega pointing to the right. The fact that they don't agree means they're pseudo vectors or axial vectors. And generally, you're not going to have to do a darn thing with that this whole course. But as you go on and maybe go further into kinematics, or excuse me, into statics and dynamics, you might have to run into dealing with pseudo vectors and axial vectors. So it's just something you need to know about now, just in case it pops up all of a sudden and you start getting things off by a negative or off by direction, and that's going to be the result. And the cause of it more than likely. So just keep that in mind. The section 10.3 is where they start to do more of the straightforward kinematic calculations instead of the stuff that we've been doing. So let's look at example 10.6. Now in 10-6 it says centrifuge acceleration. A centrifuge rotor is accelerated for 30 seconds. I'm going to say delta t because it sounds like a duration is 30.0 seconds. So I'm assuming we're going to get 2 sig figs out of that. A centrifuge rotor is accelerated for 30 seconds from rest to 20,000 RPMs. And RPMs mean revolutions per minute. They want to know A, what is the average angular acceleration? So A bar, oops. And B, they want to know through how many revolutions has the centrifuge rotor turned during its acceleration. So theta, I'm going to write theta sub rev equals question mark. Okay. So here's our chance to use some of our kinematic equations. What I want to do right off the get-go is figure out in radians per second what is this angular velocity. So A, they want to figure out what alpha is, and alpha average is supposed to be omega minus omega zero over just plain t. Remember, this is alpha bar equals delta omega over delta t. Well, the omega final is 20,000 revolutions per minute, and I'm going to end up dividing that by 30 seconds. So that's not going to give me units that are very helpful. So I have to switch the radian, or excuse me, the revolutions to radians, but I also have to switch the minutes to seconds. So I'm going to take and multiply by 1 minute on top and divide it by 60 seconds on the bottom. But additionally, I'm going to put one revolution on the bottom and make that 2 pi radians on the top. And then, of course, when I do that, I'll subtract 0 because that's the initial angular velocity. And then I'm going to divide all that by 30.0 seconds. So when I do the 20,000 times 2 times 3.14159 and then divide that by 60, I get 2094.39, and that's radians per second divided by 30.0 seconds. So alpha bar, I'm going to divide that now by 30, and that gives me 69.81 radians per second every second. Now, I really only had two sig figs at best. I'm not sure about that 20,000, but I'll assume I at least had two. So we're going to call that the average acceleration, the average angular acceleration, 69, roughly 70 radians per second per second. Now, for B, they want to know through how many degrees does it actually, or through how many revolutions does it actually rotate. So there's a couple ways we can do this. Uh, we can say theta is equal to 1 half alpha t squared plus omega 0 t plus theta 0. And of course, we can always make, just like we did with the x 0, we can always make theta 0 0. In this case, the angular velocity was initially 0, so that term goes to nothing. But now we can go ahead and calculate what theta is using alpha that we just calculated. If we do that, though, it's going to come out in radians, but in this case, we actually want it in revolutions. So then we have to do a unit conversion, and that's fine. So I'm going to say theta is actually equal to 1 half of 60, oops, 1 half of 69.81 radians per second every second times 30 seconds squared. And this is going to give me theta equals a certain number of radians. That's times zero point 0.5 times 30 times 30. And that gives me pi times 10 to the fourth. So that's 3.14159 times 10 to the fourth, and that just comes out in radians. Now I can put this over 1 so I can prepare for a unit conversion. And what I'm going to do is say pi radians is equal to 1 half revolution. Okay, I had to do the 1 half. Sorry about that. That's because I chose pi instead of 2 pi, but it's okay. The reason why is I see that this is pi times 10 to the fourth in the numerator. So if I just divide by pi, I know that's 1 times 10 to the fourth. And then that's, of course, 10,000. And then 10,000 divided by 2 is 5,000. So it should be 5,000 revolutions that it goes through. And that's exactly the right answer. You could have also done this by leaving the alpha in revolutions per second instead of revolutions per minute and then plug it in there and it would have came out automatically. So if we did it that way, we could have done, oops, running out of time. We could have done 1 half times, in this case, it'd be 20,000 revolutions per minute times 1 minute over 60 seconds, and then all that divided by 30 seconds, that would be our average acceleration, and then times 30.0 seconds squared. If I did this, it'll come out to the same thing. I'm going to say well, for starters, I'm going to say 20,000 times or divided by 60, and that's going to give me 333. So this is 1/2 times 333.3 over 30 times 30 squared times zero point 0.5 times 30 times 30.
Where did the squared come from there? Just because it wasn't there originally. Was that left out on the first part, or
No, it was there. See, notice it was right there.
no? I meant like on where you were writing in the red
Okay,
in
gotcha.
the first part of the problem.
So what I was trying to do was plug this whole calculation here for the average acceleration. I was trying to plug it into here.
Yeah, I
So,
meant the other part where it just says times 30
oh,
seconds.
gotcha. That's just because I left this off. I see now what you're talking about. I just
Okay,
left
yeah,
that
I
off.
was just wondering if it was left off or not, or
Yeah,
I
that's
missed
me being
something.
a
Okay,
goober.
thank you.
Thanks for catching me on that. I appreciate it. All right, so that does that. Well, what I want to do is we only got like 3 minutes. I need to quickly show you something. There's a concept called torque that we're going to be using, and I just need to go ahead and get you guys prepared on how we're going to calculate it. It uses what's called a determinant, which is a cross product, which is a determinant. So I'm just going to write out that torque, this new quantity that's going to be like F, and F equals ma. So we have the summation of the forces is equal to mass times acceleration. The rotational analog of that is the summation of the torques is equal to I times alpha. But torque is defined to be the lever arm, which is a vector that points from the center of rotation of whatever you're trying to turn to the point of application of the force. So that's the lever arm vector, r hat, or r, excuse me. And then we do a cross product of that with the force F. Now, you need to know how to calculate that. So here's a way. Torque is equal to r cross F, and that's equal to the determinant of a matrix. The matrix is made with I hat, J hat, and K hat as the first row. The second row is Rx, Ry, and Rz, in other words, the R vector. And the third row is Fx, Fy, and Fz. Now, I can just blindly give you this formula, but I can also explain how it's going to go on. There's a way where you can basically cover up an I hat, and that means if I cover up the I hat, then the vertical column on the far left has to disappear, and the horizontal row on the top has to disappear, and I'm left with the Ry, Rz, Fy, Fz matrix, and then I take the determinant of that. Uh, I'll show you that, or you can look at that on your own, but I'm just going to go ahead and write down the results. When I have the I hat, what I do is I get RYFZ minus RZFY. And when I have the J hat, now in this case, I have to do RZFX minus RXFZ. And then the K hat is going to be RX Fy minus RYFX. That's one formula for how to do it, and that works every time. Okay, so you're welcome to use that, and I think that's even the version I have on your equation sheet. But I'll cover that more. I just wanted you to be able to do this calculation. I will tell you that the cross product A cross B is also given by the magnitude of A times the magnitude of B times the sign. Notice how different that is from the dot product. The dot product was A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And both of them were something like this, where you had A and B tail to tail, and then theta was the angle between them. They're both right. That's the way this is supposed to work. So hopefully that'll help you a little bit. And that's it. I'm going to let you guys go. It's time to go. I'll wait for the last person to leave in case anybody has any questions. But make sure you chat me your first and last name if you haven't already. And I will see you all next time. Colin or Ryan, do you have any questions?
No, I was just finishing writing this down.
No problem. I'm going to post some videos from my YouTube channel where there's like 40 different ways you can do to calculate this cross product. And ideally, it'd be best if you figured out a way to do it where you didn't have to just plug in a formula. That's really wasteful time. But if you just learn how it's done, it'll make more sense. So that's why I'm going to post some more videos on our YouTube channel. I mean, on our Canvas page.
Thank you.
You're welcome.
Take a look at this.
That looks like it. And that's it. Bye, everybody.